Let's learn math, because math is the ish, as the kids say. So before we do some problems, we're going to do some, we have a few more tests to state. So we have 2 more tests. So we talked about this. We alluded to these on Friday, but then we got into some examples, and we had some good talk. But this leaves us with what's called the ratio test, and a very close relative of the ratio test, which is the root test. So, okay, so here's the thing. Here's what I'd like you to think about if you want to like actually think and learn, or you might just want to daydream and take a nap while I'm babbling. What we know is this, in the general gist of things, here's what we have. We're studying these creatures. So let's consider some generic series, which I'll denote a sub k. We'll say k starts at 1, but we know it can start at any integer value that's positive or 0. And so this is some number we're calling a sub 1, plus some number we're calling a sub 2, plus some number we're calling a sub 3, etc. So here's what we know. We know that if this thing's going to converge, that we know these terms, that the terms have to be approaching 0. That's what we know. Which means one of the things we might try to do to get a gauge on what converges and what doesn't is we might try to sort of measure how something goes to 0. So what I mean by that is look at, we had examples of this where we know that the harmonic series diverges, even though its terms go to 0, but these P series converge. And the fact of the matter is I found this on the web. Oh, I hate when she does this. Siri. See, this is what happens when we start saying series over and over again. Siri thinks I'm trying to flirt with her or something, right? Siri, do you like when I pitch woo? Anyhow, while I'm on it, let's delete all these emails. I keep getting emails from Trumpster and Biden all day today. This is amazing. What these last 2 tests do, the way you can think about them, you don't know how. Don't. So here's the way we want to think about it. We know if this is going to converge. I guess I should do correct English. Is going to converge. We need the terms to go to 0. So what we say is there some sort of way we can measure these things, how these terms go to 0, and the ratio test and the root test sort of do that. They sort of look at a way, okay, we're going to sort of quantify how these terms behave. And so here's what we have. No, this is, oh, you mean here. Yeah, that should be infinity. Sorry. Okay. So what I mean by measuring speed of how things go to 0, let's just look at Desmos for a second. And we talked about this a bit when we did our integrals, particular our, what are they called? I'm losing my mind. When we did our improper integrals. What happened to my webpage? It disappeared. I got an idea. There we go. So let's share Desmos. And what I mean by how something goes to 0, look at 1 over x. So what I mean, if in particular, put your finger on this curve, and as your X values, your inputs get big, look at the Y values, the outputs are getting close to zero. And so when I say we want to measure how quickly it's going to zero, compare that with something like this. What you'll notice is the red curve, 1 over x squared, is actually beneath the green curve. And it's getting closer to the x-axis, if you will. It's quicker than the green curve, right? If there's a race to try to get there, the red looks like it's winning because it's lower. And then we can even compare that with things that aren't these sort of rational functions. What if we did something like e to the negative x? Look how quickly this creature, if we zoom in, you'll see that this guy's getting closer even before these guys do. So what we're going to do is, what the ratio and root tests do is they kind of sort of think about asking, how are these numbers, how rapidly are they getting small? You could sort of think of it that way. And so what the root ratio test says is, it says we're going to look at the ratios of consecutive terms. And if they have a certain property, then we know we're going to get convergence. So here we go. So this is the good old-fashioned ratio test, one of the most useful tests there is. Suppose the limit as k goes to infinity of the following thing. So look, what we're going to do, this is why it's called the ratio test. We're going to look at ratios of terms. So suppose this creature is less than 1. Then this series converges and it's very strong. It converges absolutely. If the limit is greater than 1, it diverges. The series diverges, I should say. And if the limit is equal to 1, the test is inconclusive. It doesn't apply. You need a new test. So think about what this thing is saying. This is saying it's taking the terms, and if you go far out in the series, if you look at consecutive terms and their ratio, notice this is telling you, it's sort of quantifying how quickly these numbers are going to zero. Because if the numerator, what's the only way that a number can be less than 1? Well, the numerator has to be smaller than the denominator. So first, this is telling you that it's decreasing. And it's also sort of telling you how quickly it's decreasing. So the best thing we can do is we can just do some examples. So let's look at some. So number 1, we'll take this series. How about the series k over 5 to the power k? K starts at 1 and it ends at infinity. So the first few terms, let's write them out for practice. This is 1/5 plus 2 over 25 plus 3 over 125. I claim that this converges. So let's verify why. change colors because we need to see this in all its glory. So we will use the ratio test. So here, what is the a sub k? A sub k is k over 5 to the power k. And that means that the k plus 1 term is k plus 1 divided by 5 to the power k plus 1. So this is the first thing that you have to get comfortable recognizing. Many students struggle with this. We just, whatever it is, when we're babies in calculus classes, we stink at subscripts. We have a hard time understanding these things. It's just what we do. It's not you being stupid. It's not me being a genius. It is just normal people do not have enough experience at this point to readily, to not mess this up. So you got to get comfortable with this. All right, so let's look at what happens. So we're going to apply the ratio test. So also, what is a sub k plus 1 over a sub k? Well, let's take the limit of this because that's what the ratio test tells us to do. Notice I do not need absolute values because every term is positive. These are all positive numbers. So the absolute values are redundant. You're left with k plus 1 over 5 k plus to the power k plus 1 over k over 5 to the power k. So this looks ugly, but you learned in elementary school, middle school, how to simplify an expression like this. This just becomes k plus 1 over 5 to the power k plus 1 times 5 to the k over k plus 1, excuse me, over k. So I'm multiplying by the reciprocal of the denominator. And what happens here is you get lots of cancelizations. This cancels with one of these. And so what you're left with is you're left with a very straightforward limit from calculus 1. That is, you're left with the limit as of k plus 1 over 5k. And of course, I feel bad we're squishing this in. This limit is just 1/5. That's good, Emily. You should be voting. I don't know why I just read your chat right now, but so since this limit is less than 1, the ratio test says it converges. And not only does it converge, it's what we say absolutely convergent. Now, I don't know what the sum is. I can't tell you what it converges to. Of course, if I go to a computer or if I suffer with a calculator, I can probably get a good idea by adding up partial sums. Does anybody have a question about this? What do you mean, forget it?
No, in order for you to get 1 over 5, right? You just separated those two. K plus 1 over 5k to k over k plus 1 over 5k.
You could do it that way. So I think you're asking, hold on, let me make sure I understand what you're asking. Let me go to the next page. So I think you're asking, how did I reason? No, undo. So I think you're asking, how did I reason this? This limit? Yeah, I mean, no, the way you're doing this is just one of those, look, these are polynomials, right?
No, the plus one.
No, the plus one's downstairs. Did I do it wrong? Oh yeah, the plus one's upstairs. Okay, yeah, okay. It's still, okay, I see what you're saying now. Oh, I see how you're reasoning it. You're just reasoning it more, what you did is not wrong. You're saying you want to reason it this way, which is not wrong. You want to write this as k over 5k plus 1 over 5k, right? I mean, that's not wrong. And then this is just this limit. This is 1/5 plus 1 over 5k, which is just 1/5 plus 0. I mean, that's fine. You can definitely do it that way, but you don't even need to go that far. I mean, if you're at this point, look, we talked about limits like this back in Calc 1. Since the degree of the numerator and the denominator are the same, it's just the leading coefficients, 1/5. I think you guys are even taught that in like algebra when you're doing horizontal asymptotes. They tell you to look at the leading coefficients. I don't know if that makes any sense, but you can do it that way. But you're not wrong. This is correct reasoning too. It's just not necessary. You could do it. I mean, that makes me happy, but it's not necessary. This limit would be an obvious limit. All right. Does anybody have any questions about this? Maybe I should move this. This looks silly. All right, so we get convergence. Okay, let's do another one. How about this series? Let's get one that alternates. Well, here's a good. Here's a good one. So many of you might not remember with this k, maybe you've never seen it before actually. So I'm gonna have to explain this in a second. When I plug in 1, I get 1. Then it's minus 1 over 2 plus 1 over 6 minus 1 over 24 plus this pattern goes and like this. What do you mean by I? I'm not using I, I'm using K. I'm not sure what your question is or your comment. Yeah, so that's exactly what my next point is going to be. This notation, for those of you who aren't sure about it, note K, this reads K factorial. And what does it mean? Well, if you're not familiar with this, it means it is defined by K factorial equals K times the number that precedes K, which is K minus 1, times the number precedes that, which is K minus 2, and then that pattern goes all the way down to say 3 times 2 times 1. So on the next page, we'll list some of these out for you. These things, if you're not familiar with them, they will show up a bunch in the remainder of this semester. They're very common in many branches of math and computer science. It's a shorthand. This is a shorthand for factor, a type of product that shows up a lot. Just like exponents are shorthands. Well, now you know. It's a first for everything, Emily. So You know, a very natural way this shows up. Suppose I have a bookshelf at home and I have 5 books, and I might ask myself, okay, how many different ways can I rearrange the books? Well, for the first book, I have 5 options because there's 5 books. Well, once I place the first, how many options are left for the next one? 4. And then for the third one, 3, 2, and 1. So it turns out that this factorial shows up when we're trying to study counting certain things, and it also shows up in calculus all the time. If you've ever taken prob and stats, you should have seen it there. Okay, so just let's list the first few if you're unfamiliar with them. For example, 1 factorial is equal to 1. 2 factorial is 2. 3 factorial is 6. And by the way, how am I getting 6? Let me be very clear if you're not picking up the pattern. This is 3 times 2 times 1, which is 6. And then 4 factorial is 4 times 3 times 2 times 1, which is 24. 5 factorial is 5 times. Notice that here's another shortcut you can pick up on. This is 5, and then this is times 4 times 3 times 2 times 1, but this is just 4 factorial. So you really get that 5 factorial is 5 times 4 factorial, which becomes 120. That's correct. So there's a very nice pattern that you see. So the pattern is k factorial is always equal to k times k minus 1 factorial. And then this comes in handy all the time. And then there's another thing that we define, and it might not seem to make sense for you. We also define 0 factorial. So it turns out that if we take the number 0 and we want to make sense of this, we say it's equal to 1. Now, factorials, as I said, are very, very common going forward. Now, you might say, well, how do they show up in calculus? Well, think about a polynomial. If I differentiate a polynomial, say I take x to the 4th, differentiate it once, I get 4x cubed. Differentiate it again, I get 12x, right? To the 2nd, differentiate it again, so you get 4 times 3 times 2. Do you understand where I'm heading at here? So these factorials turn out to be ubiquitous in many ways. All right, so let's go back to the problem. And also, let me say this, and I'll write it in a different color. Anytime you see a factorial in a series, so k factorial in a series screams to use ratio test. So you're looking for, if you're looking for things that to give you are sort of signs when to try a test, you see a factorial, that is like saying, yo, use the ratio test. And the reason it is, there's a few reasons, but this pattern right here that we have, it often, things look like they're going to be ugly as you know what, and they turn out to cancel out. So what is often ugly simplifies pretty simply. All right, good news. Great. You guys are the best. No. Am I going to make you do it with large numbers? No. Oh, by the way, Emily, and this is, any calculator knows this, so don't freak out over it either. If I go to Desmos and I say Desmos, is everybody seeing Desmos? Yeah. If I say 5 exclamation point, it knows exactly what that means. See? It knows what this is. If I go to Google, and I say 5 exclamation point, it knows exactly what I mean. So you don't have to do these by hand. I mean, God almighty, no. You should know the first few, and it'll make your life easier if you know the first like 5, 6 of them. because they show up a lot. So if you have it right in your head, it's quicker than having to go to a calculator. Be that like kid who goes to a calculator 6 times 7, and you look like my dad touching the screen like. Yeah, see, that's what I like to see. That's the spirit, Emily. Positivity. Everybody needs to be positive. There's only 3 peasants in this room right now. How many people are watching from home, if they're even alive? 12. Boy, our attendance is, what happened, everybody? Calc 1's the best. I mean, I don't even know who half the people are. I'm like, what the F? What did kids say? WTF? What the frig is the that's what they would say in church, right? Can't cuss. I always ask that, but who decided that these words are bad, right? Like if I swear in English, but I'm in another country that doesn't speak English, am I cussing? These are the questions that are philosophically important to me. You never think about these things? By the way, it'd be a good time for me, since we're on this. I once went to this conference, and there was a gentleman there who's an expert in linguistics and the language, and he did this presentation on cuss words. And I'll tell you what, it was so educational. He talked about where they came from, when they became bad, and why, cultural things. It was fascinating. It really made you think. But I still think it's funny that like certain words, I don't know. Then again, my mom gets mad at me if I cuss, so you shouldn't cuss, right? Does anybody say cuss? I know, that's what I said, Emily. It was fascinating. I think this dude wrote books too. I'll have to find out who he is. Maybe I'll give extra credit if I find his YouTube stuff and you can watch it. It's fascinating. Like just learning like who decided these were offensive, why they're offensive, where did they start from? I think you guys kind of know, like the F word's amazing because it can be used as like an adjective, a verb, and that like you use it, not that you should swear, but is there an equivalent now? I think in England, isn't bloody like a bad word? Like you don't say it. I don't know. Is bloody okay to say? For like back home, if you were a kid in school and you said bloody back in Kenya, would they beat you? No, I don't know. That's exactly. So Fogger, you should. I tell you what, when I was in high school, I wish we would have had like technology like we do now. In Spanish class, we used to have to we'd do these things they called conversation points. Senorita Pope, you'd have to go home and then you'd come up with something and you go up to her desk and have her say something to her. And once we always wanted to learn cuss words, but you'd have to go find a Spanish to English dictionary or something. Like now, you could just go to Google Translate and do it. That was always fun. Hey, I don't know the culture, man. Yeah, I think bloody does, but I'm not positive. Well, it's like the other F word that we use here is, I guess it's turned into like a slur for certain groups of people. I don't know how I'm supposed to say it, but in England, it's like a cigarette, right? So I don't know. I don't know how you decide when. Here's what I say. Just don't offend anybody. Of course, then there's those people who say, well, everything people do now is offensive, right? So I don't know. I don't know. It's a strange world we live in. It's very strange. I agree with that too, Muhammad. Like, you ever just drive down a road and oh my God, that chat got massive. That's a huge chat. Sometimes I'll just be driving down the road and sometimes it just feels good to lay out a grand old, you know what I mean? Like, just feel good. Let's release that. You know what I do? And the problem is, and I wish you guys were all in here, I'd share a schematic because I've done this before. The way my neighborhood is set up is we have like our bathroom has a window and then it overlooks our driveway and then we're up above the neighboring house. Now, we're not right close. I mean, it's a decent distance, but there's no doubt in my mind when I'm singing in the shower, which most people do, I'm either rapping or singing. I'm doing something, usually cussing because that's what all music is now. And I remember being in like a younger teenager when I lived with my parents. My mom was like, what are you singing? And I'd be like, rapping and saying all these bad things. And I wonder if my neighbors are probably like, what is wrong with this weirdo? Yeah. Anyhow, back to math. You guys are fun. I really like this class. All right. So anyhow, let's regroup. We're reminding those of you who've learned this before what a factorial is. If you've never learned it before, well, now here you know. You can Google it. It's not hard to learn. And it has some nice patterns. So, very well. Let's go back to our problem, which is this creature, negative 1 over k factorial. All right, so back to the problem. So back to, oh, I don't want red. Back to this creature. Which again, as I said, this is when you k is equal to 1, this is 1 minus a half plus a sixth minus a 24th, blah, blah, blah. So here, what is a sub k? Here, a sub k equals negative 1 to the power k plus 1 over k factorial. And the absolute value of a sub k is just 1 over k factorial. So here, having these absolute values, they save you a heartache because they just kill the negative. They kill it. So one of the things you might say is, well, why don't I use the alternating series test here? Well, I guess you could, but it turns out the ratio test is easier to apply. So thus, let's take the limit. The limit we're interested in, the limit is k goes to infinity of a sub k plus 1 over a sub k. In absolute value, this is the guy we want. This is just equal to 1 over, oh, I guess I need my limit in there. It's equal to 1 over k plus 1. Now this often will mess with your brain as well. This is 1 over k plus 1 factorial divided by 1 over k factorial. So this numerator will mess with you. You gotta think about why that's true. Now, if you're on to what's going to happen here. That's why we always talk about these factorials as being very useful, because the notation, the way we do it, things cancel and it turns out to be easy. If I rewrite this, this is the same as k factorial over k plus 1 factorial. But, if I go to the previous page, this cool pattern makes everything work well for me. This pattern, if I apply it to k plus 1, so again, this pattern, if I rewrite it, I can apply it to k plus 1 instead. So if I take this creature, and I can also say that k plus 1 factorial is equal to k plus 1 times k factorial. Same thing, right? It's just switching our indices. So convince yourself that's what? So I'm going to apply this fact right here. So that means that downstairs here, that means downstairs, if I want to cancel this properly, I have k factorial. Then downstairs I have k plus 1 times k factorial. And then this is just a very straightforward limit, because I'm left with 1 over k plus 1, which is 0. And so we get convergence. So this limit is less than 1. It's less than 1. The ratio test says we converge. Say that again.
Can you just explain again how you use those to get?
How did I go from here to here?
No, that part, right?
This right here? Okay, so yeah, so the question was, how am I going from here to here? So don't ignore the limits and all that stuff. Go back to 5th grade. Oh,
I mean from the top part to the,
yeah. From here,
no,
from this?
yeah.
Well, what's the k plus 1 term? It's 1 over k plus 1 factorial. So look, don't get afraid. If I say what's the 100th term? The 100th term is 1 over 100 factorial, right? So what's the 101st term? Well, that's 1 over 101 factorial. So the kth term is 1 over k factorial. That means that the kth plus 1 term is 1 over k plus 1 factorial.
We went the minus one.
Again, so where's the minus 1? I don't need it. I'm taking absolute values. What's the absolute value of a minus number? The positive, right? So that's the point. So the question was also, where did the minus sign go? Well, I don't need it because if I take absolute values, it's always 1. And that's a good thing to remember. Does that make sense now? You sure?
So for the AK, when you write AK down, right?
Yeah.
Why did you put the minus seven?
Where at? Here? Because I'm writing what a sub k is. This is a sub k, this. But I'm telling you, if I take this and I put absolute values around it, it's just 1 over. Does that make sense? By the way, what this tells us is more. So we get 2 for the price of 1 here. So we get that this series, -1 to the k plus 1 over k factorial, and this guy, 1 over k factorial, both converge. I sure can, yeah.
So when we use the alternating,
I'm not using the alternating series test.
no, but don't you think when you use that it's easy? Because when you find the limit of 1 over k,
Oh yeah, you could have used the alternating series test here, yeah. You could have.
but that's easier, right? Because
You might argue that, yeah. I mean, that's personal preference. I mean, someone might say the alternating series test is easier. That's true. But I'm using this as, I mean, there's often times where more than one test applies. But by using the ratio test, I got another thing for free. I also got that the absolute values converge. And here's a cool fact. It's a consequence of this.
But those two say different somewhere.
Oh, absolutely, yeah. So we'll show you how to do this at some later point, but here's what's even more interesting. In fact, we will show later, and this is really cool, the sum from k equals 0 to infinity of 1 over k factorial, which is 1 plus 1/2 plus 1/6 plus 1 over 24 plus 1 over 120. We will actually show that this thing equals E. Now you can get a feel that that's true just by going and adding up some partial sums. Actually, I lied. I'm missing a term. If I start at 0, this is 1. Let me be more careful. If I start at 0, I get a 1. Plus 1 equals that. And by the way, you can, let's also say that it converges quickly. What I mean by that, well, look at the first few terms. Let's just do the first 5 terms.
Professor,
Yes.
like this is like famous limits, right? We say E is equal limit n to infinity, parenthesis 1 plus 1 over n over n. Like,
Yeah, well,
did you
I
understand?
mean, that's
Did
one
you
way. You
understand?
can define E in lots of ways.
Like this is its definition, you know,
Well,
so we
how
can.
you define it. That's not necessarily true. I mean, you have to think about how you're defining the limit, though. What I mean by that is there are a handful of ways to define E. Many people, you know, probably the best way to define E is to define it as this. By the way, I guess I should have. I have to be more careful here. I have a slight error. This should not be equals right here. It should be the ellipsis and then equals. This is probably one of the better ways to define E, but you can't define E like this if we're going to teach calculus to first-year undergraduates, because we need to you can't wait for series to have a notion of what E is. So how do we teach E? We usually introduce it in like a pre-calculus course as this special number that you'll learn about later. So yeah, but this is one of the definitions. There's lots of equivalent ways to define the number E. By the way, if I add these numbers up, if I go to a calculator and add up the first 5 terms, so the first 5 are 1 plus 1 plus 1/2 plus 1/6 plus 1/24. You end up getting 2.71. Well, I shouldn't say you get that. Let's be more careful. It's approximately that. So we're all, if we round, we're accurate to 2 decimal points already. So if you go, Zafalgar, for example, if you went to like the Wikipedia page, and you know, let's just for full disclosure, let's do that. Let's go and let's just Google the number E. Well,
Like we can find it from Taylor series, like
well,
E.
right, but we don't know what a Taylor series is yet. That's the point. So you'll
Like
see.
you and me, you and me know. So if that's so. So
I mean,
when we
you can't define a Taylor series until you know what a series is. And by the way, if you look at the way I've written it, I'm also foreshadowing. In fact, we will show this. How will we show that this is true? This is true. We'll show it because once we learn Taylor series, we'll know it's true. But you don't need Taylor series to define it this way. You can use the theory of series to define it. There's lots of, the point I'm trying to make is there are many ways that you could define the number E. You'll notice how Wikipedia defines it. They define it as this sum that I just said. They're using N, but I'm saying K, it doesn't matter. But there are tons of definitions. The way we defined it is we defined it as, in Calc 1, we define it in this interesting way. We define it as the number that gives us something we want. So we define it in a very roundabout way. In particular, we define it using this notion. So, you know, it's from a theoretical purpose, the way we define E in calculus is probably not ideal, but it allows us to use E early on. And by the way, it's worth pointing out, if you look at calculus books, notice most calculus books have two versions. They have a calculus, and one will say early transcendentals, and one will not say early transcendentals. And so a book that says early transcendentals, that essentially means they're going to introduce E early. Books that don't have early transcendental, they wait until later on to introduce E because they define it using fancier ways, if that makes any sense. It doesn't matter really how you do it. Right now, we're not here to learn the theory of calculus right now. We're here to learn calculus as a tool for science and engineering, and that's it. If you want to learn the theory of calculus, you take upper level courses. But it is worth pointing out that even though most series it's hard to tell the exact sum, some of them we will be able to. We'll be able to tell you this exact sum. It's pretty interesting. And by the way, it's also worth pointing out, the one we had before, what was it? The sum, what did we start with? -1. What was it? To the K, let's say -1 to the K. So the original series that I gave you, and this is pretty fascinating too, we'll be able to show this.
We don't see the screen.
So we actually will be able to show you this. Well, you'll be able to deduce this, I should say. So the series we started with, I know we did. So if we take this guy, -k + 1 over k factorial, if we started at 0 as well, you'll notice that when it's 0, you get -1, and then it becomes +1. Because when k is 1, you get 1 over 1, and then -1/2 plus 1/6 minus 1 over 24 plus 1 over 120, etc. This guy actually equals, believe it or not, 1 over E with a minus sign in front. Now, again, if in order to see why this is true, we need to learn more stuff, but we will see why in a few classes. All right, anyhow, there you go. Very good, very good, very good. All right, so Let's move on. Very close in. Oh yeah, what's up? Not done? I'm like cold right now. Put my sweatshirt. The stupid exhaust fan above me is giving me pneumonia or something. I shouldn't joke about that in these times that we're in, where everybody being sick. Take your vitamins, wash your hands. Good? All right, so then we're not going to spend much time on the next thing because it's very similar, and it's very much related to the ratio test, and it's called the root test. Now, the thing's called the root test, which means a sure sign you might want to use it is if you have roots. But you got to be a little careful because the root test uses roots. So maybe instead of roots, you say, oh, if I have power. So we'll get to that in a second. Anyhow, so suppose, again, we're going to go back to this. Suppose the limit as k goes to infinity of the kth root of the absolute value of the kth term. Suppose this is less than 1. Then the series converges absolutely.
Professor, I've got a question. Do we record this class or?
Say that again?
Do you record this class or?
I am recording it, yes. So the series is going to converge absolutely if we have this nice power thing happening. In particular, if the kth root of the kth term is less than 1, we're feeling good about ourselves. So again, you want to use some educated reasoning here. If the ratio test takes ratios, then, you know, in the root test, it uses these roots, then just by the way they're defined, they give you a glimpse or an idea of what you might want to use when you're dealing with them. So we're going to do an example here in a second, and hopefully that example helps to illustrate it. So just like the ratio test, though, if the limit is greater than 1, the series diverges. If the limit is 1, the test is inconclusive. Just doesn't apply. Say that again?
Does that mean that no other test will also apply?
No, it doesn't. It does not. It means you need another test. So if the root test or the ratio test doesn't apply because the limit's 1, that means you need to try another test. It doesn't apply. It doesn't give you any information. It could converge. It could diverge. And there's examples that illustrate both. So if you want to get a feel for that, try the ratio test on the harmonic series and then try the ratio test on 1 over k squared. So if you want to get a feel for what do I mean by that. The best way to learn is to investigate. All right, so let's look at an example here. So let's say this series. The series k goes from, say, 0 to infinity. Start at 0. Of I don't know. How about 2k squared plus 5 divided by 3k squared minus 1 to the power k. So what is this guy? Let's write out the first few terms. When k is 0, here, let's make it real easy. Let's call this plus 1. Don't have to deal with any shenanigans. When k is 0, we get 1. When k is 1, I get 7 over 4. When k is 2, I get 8 plus 5 is 13. And then downstairs, I get k squared would be 4 times 3 is 12. 12 plus 1 is 13, right? K is 2, so then I get 13. So that's the number 1 really raised to the second power. Yeah. Let's do one more for fun. The next term, when k is 0, 1, 2, when k is 3, I get 18 and 5. What is 18 and 5? 18 and 5 is 23. And then 27 plus 1 is 28. And that would be to the third power. So this guy will converge. And we're going to show you why. One thing to note is look how these terms, the first term is 1, the second term is bigger than 1. The third term is 1, and now it looks like they're all going to be less than 1. Provided I didn't make an error, of course. Excuse me. Okay, let's use the root test to show why. Now, why is the root test, you know, when I look at this, really the only thing that even seems to make sense to me is the root test. Because I got something ugly raised to a power. And so what I'm hoping is that the root test, the kth power will be killed by the kth root. So let's use the root test. So since, what is a sub k? A sub k is equal to this creature. Then what is the kth root of the absolute value of that? Well, the kth root, everything's positive, so the absolute values are redundant, but the kth root will kill. The kth power.
The limit of that gives us like,
yeah, and now the
2
limit
over
is very
3.
straightforward. Again, we don't have to do much reasoning at all. That limit's 2/3. So maybe we should write this, since this and this. And then the root test guarantees convergence. Why does the root test guarantee convergence? Because this limit is less than 1.
So, Professor, we have finished all these 7 uh, tests, right? We have covered all of them. We like I personally need tricks when we need to use the proper test, because we know when to use root test, we know when to use ratio test. The rest of the 5 of them, like they are absolutely crazy. Like I don't know when to use another
Well, that's
test.
the point. It's experience. So I think the question you're asking, the question is, how do you know which test to use? And look, I don't have a good answer for that, and I don't think there is a good answer. There are certain themes that arise. Like if you see factorials, it's almost always going to be a ratio test. If you see powers, you should think root test.
Yep.
And then you also don't forget the ones we talked about originally. Like you should be able to recognize a geometric series. Also, if something looks like a p-series, you should think, oh, maybe comparison test or limit comparison. So these are the themes that you hopefully will pick up on. Yeah, that's exactly right. Practice, 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 practice. In the words of the great Allen Iverson. There's no checklist I can give you that says if you follow this checklist, it'll be easy to do series. They're not. Series are they're difficult. It's conceptually challenging. I mean, most students take calculus 2. They don't even really quite understand what all this means. You just kind of memorize rules and apply them, and you still have a hard time understanding that this series is really the limit of partial sums and stuff. So there's no rule book that I can give you that says if you follow this rule book, you'll get every series. That's really not how it works. Yeah. Yeah, I know. And look, Zafalgar, I hear you, man. I do. It's there's no, like I said, there's no cookbook that tells you exactly what to do. There's just not. It's just practice and familiarity. One of the things that you can sort of, the way I would encourage you to think about it is first think, is it geometric? And then if it's not, then you say, okay. Then you ask yourself, so maybe I'll write this down. Here's sort of my strategy. So the big question always is what test to use. Or a better way of saying it, what test to try first? Because often, whatever you try first doesn't necessarily work. So here's the O'Grady strategy. First thing I ask myself, is it geometric? And if it is, then I'm done. The next thing I ask myself, is there a factorial? And then if so, try ratio. The next thing I ask myself is I say, does it look like a p-series? And then if so, comparison or limit comparison. Now, when I say look like, it's not going to be a p-series. If it's a p-series right away, you're done. Like I gave you, some of the homework problems are just p-series. You don't have to do anything. You just tell me it's a p-series and it either converges or diverges. That's all. And then once I go through this thought process, then I start thinking about, can I use the divergence test? And then I say, if that doesn't get me anywhere, then I go integral and root. And then it's possible, somewhere along the way I messed up. Well, series are in general, they're difficult creatures. So you know, you don't want to get discouraged. You don't want to get sort of mad at yourself. You don't want to think you're not going to be able to figure it out. You just there you go. Yes. Sure. Yeah. You have a question?
Situation where you have 2k, like that, the equation raised to the power 2k.
Okay. Yeah.
So what would you do?
That would just be a pain. I mean, you could try the root test, but the algebra is going to be hard. I mean, it's still going to work. I mean, so the question was if this were to the power 2k, I believe, right?
Yeah.
Yeah, it's still going to work because if you take the kth root, then this would just be squared. So you can take the limit inside, and you would get 2/3 to the power 2, which is still less than 1.
So it just cancels out the k, right?
It can't, that's exactly right, yeah. So it would converge still. Because if you did it properly, your limit would be 2/3 to the power 2, and 4/9 is still less than 1, so it would converge. If I can let you in on a little secret, typically the root test is more useful as a theoretical tool, which doesn't really matter to us in Calculus 2. And the ratio test is often more useful in practice. So the practical tool is typically the ratio test. That's the one you usually use the most. But from a theoretical standpoint, the root test is often easier to take advantage of. And I don't know if that makes sense to you. So you can translate that as in Calculus 2, the ratio test is more common than the root test. How's that sound?
Now, when you use the root test in, like, let's say 4 over 5 raised to power k. Or no?
Right, but then that would just be adding 4/5 over and over and over again. So I think your question is this. So and correct me if I'm wrong, I think the question you asked was this series. So if you had 4/5 to the power k, well, why would you use the ratio test or the root test here? I mean, this is geometric, huh?
Can you use the root test? Or
Well, you could try what happens when yeah, you can. Well, let's see. Does root test, we know this is geometric. But you might big ask, but does the root test apply? Well, take the limit. What is the limit as k goes to infinity of the kth root of 4/5 the k? Well, that would just be the limit as k goes to infinity of 4/5, which is equal to 4/5, which is less than 1. So yes, it works. You could use a root test there. So yes, root test confirms it converges. So the downside is if you just use the root test, all you get is that it converges. But if you recognize it's geometric, then you know it converges and you know it's sum. So you get more if you understand it's geometric. Does that make sense? So it's not wrong to use the root test. It's just that you don't get as much information from it. Does that make sense? Anybody else going once, going twice? Someone's chiming in on the. Sure, you could turn it in whenever you want. So if the homework, I don't know when is it due? I don't know. You could turn it in whenever. I mean, just turn it in before the end of the week. I mean, we have to move on to new things on Thursday. So if you have, like I said, Becca, I'm never gonna take points off if your homework's like a week late. Now, when you submit homework 4 weeks late, then no. Well, I mean, I'll collect it, I'll take it, but I'm not going to give you full credit. Might not even grade it. I might just give you like 2 out of 5 or something, just because I'm feeling nice. But yeah, if you send it within a week or so, I have no problem with that. And if you're still stuck on these ones because they're challenging, email me. Like I said, we can't spend much more time on this because we do have to move on. Any other questions? So look, the last thing I'll say about this today is these are challenging. Do not, let it hold you down. Do not, work you up. Yeah, that's true. You could do that. Get your 5 points that way, Emily. That's right. All right, guys. Thank you very much. Have a good one. Be safe. Go vote if you didn't.